one example of K-theory versus graded K-theory. And that really explicitly shows that how much more information you would get out of graded version. So K-theory versus graded K-theory. Is versus correct? Versus.
That's okay.
And I'm going to start with, I'm going to calculate the graded K-theory and the usual K-theory of Leavitt path algebras, which associated to one vertex and two edges. So you have a Leavitt path algebra of this. Sometimes they call it L12. And I want to calculate its K0 and its graded K0. So I'm gonna just give an indication why the K0s would be that. So it's just an indication, it's not a precise theorem. Okay, so now, first of all, look, I have a map. I know that, and Muge and Rango also mentioned that in this situation, A is isomorphic with two copies of A. That was the intention of Leavitt to construct algebras of this sort. And let me just give you the map that gives you this isomorphism. So here your loops are y1 and y2, and then the ghost ones, I just call it x1, x odd. So then I'm sending A to x1a and x2a. In fact, I think this is a very nice undergrad exam questions or exercise. So let's do it together here. So I'm just sending A to x1a and x2a, and mind that xi's are the star version of y. Okay. So this is a write A module, homomorphism. Let me call it phi, and then this time I'm going to go from the direct sum to A, and my intention is that I construct this such that phi psi would be identity and psi phi would be identity, therefore A plus A would be isomorphic to A. Now, can you guess where should I go? So if I have A1 and A2, I have to send it to a single element here. Can you guess what would that be? Okay, so maybe I should remind you the relations here. So remember that, let me just put the relations. So remember the relations of Leavitt path algebras are y1 x1 plus y2 x2 is u, this u here, and then xi y j is delta I j u. And if I look at this as one, really, it behaves like one. So I just put like one. Because in this structure, U is the identity element. So that maybe show the way that I'm going to put the single element here as y1 a1 plus y2 a2. So let's do at least one side together. So I'm starting with maybe phi psi. And I get A, maybe the other way around. Psi, phi, I just start with single element A. Let me chase this. So phi of A gives me x1a, x2a. Now I'm in here, so I can write as y1 x1a plus y2 x2a. This is y1 x1 plus y2 x2a, and now I'm going to use the relation, and I get A back. Right? So that gives me that phi psi is an identity. You can do the other one. You can do the psi phi, the other one, and then here you need to explicitly use these relations to get identity. So now, what did I prove? I proved that A is this isomorphic to two copies of A. Let's go to K0 now. Remember K0, I'm collecting all the finite iterated projective modules here. In particular, there is A, this order unit. sitting in here. But look what happened. I know A is isomorphic to 2 copies of A. So in here, I get A is isomorphic to A plus A. But now I'm working in a group, so I cancel it. So A is in fact 0. So this is not a proof, but indication that the K0 of this Leavitt path algebra is in fact 0. And if I want to use the formula Muges told us, is that you look at the adjacency matrix of this, which is just 2. Remember, you look at the adjacency matrix, you transpose it, you subtract the identity, and then you get the co-kernel of Zn to Zn, and that gives you the K0 of your Leavitt path algebras. In this situation, so the adjacency matrix is 2, identity is 1, so that means 1, n is 1, so I have just like Z co-kernel is Z over Z, which is 0. So I got it. So that's really the proof. If you believe me that this is the real formula for K0, this is the proof, and this is justification. All right, so the K0 really, in a way, doesn't give you anything. Now let's look at the graded K0 of this specific example. Now let's go back here. So I'm sending A to x1a and x2a. All right. Now, this is the nicest part of the whole theory. Can you follow me here? So now, look, now I work with the graded homomorphism. Right? So pick some homogeneous element. Remember that just if you have a homomorphism of graded modules, it has to push the components, corresponding components to each other. So it has to push m alpha to n alpha. Remember, the pieces have to go through. Okay. So now, imagine I get here some beta. So this has degree beta. Now, what is this degree? If you remember, the canonical grading that I give here is the degree of y is 1, the degree of its growth is -1. And that gives you a z grading on the Leavitt path algebra, right? So I assign the length 1, as you see, 1 to these yi's, and then if you go backward, I consider -1. Okay. So this has degree -1. I'm looking at the a beta, so the degree of a is beta. I'm pushing it here. What's the degree here? Beta -1. Okay. So the degree here is beta. The degree here is beta -1. Degree here is beta -1. But I really, if this is supposed to be graded homomorphism, so the beta component has to go to the beta component and beta component here. How should I fix this? Because at the moment it's going to a beta -1 component of A. So if I shift it a bit with -1 and -1, then I'm okay. Because remember the definition, the beta component of this is the same as A beta -1. So see what happened. I just proved that, and the other way around, the exact same thing, the other way around. So I just proved that as a graded module, A is isomorphic to this thing. So let's go to the graded ring, and graded Gortenic group. So then A is isomorphic to 2 copies of A -1. So this is the difference. Previously, maybe I just write it. So A is 2 copies of this. And now the difference, previously A was 2 copies of A. That's why I canceled and A would be 0. But here there is no cancellation, right? So all I can say is that A is 2 copies of A minus 1. Exactly the same, A minus 1 is 2 copies of A shifted by minus 2, and so on and so forth. So if you think of this as 1, this has to be 1/2. This has to be 1/4. So that's, again, an indication that the K0, the graded version of A, is not only not 0, in fact, it's a very, very big group. It contains 1/2, 1/4, 1/8 because of this. So very, very big. And not only that, remember this is not a module. So there's an action of Z, or if I, so maybe I just write it here. And we know now the K0 graded of A is a Z gamma module, right? But in this particular case, gamma is Z. So Z, this grouping, I can write it also, I can present it this way. So K0 graded of A here is a Z x minus 1 module. And now how the action works. So if I add x to A, these are, again, you have to sit there and see all these happening, but just an indication. When I multiply x with A, that means I'm shifting A1 with 1. And that means I'm multiplying, this is the same as A plus A, because of this. And this is 2A. So you see the action of x on an element is multiplying by 2. So pretty good. Previously, I got nothing out of K0. Now here I get a massive group. So that's why, let me just put the conjecture here. Maybe, just maybe, graded K0 would classify the Leavitt path algebras, and the claim is it classifies all the graphs. So let's do it for finite first. Then this Leavitt path algebra is isomorphic to this one, in fact graded isomorphic, if and only if this green broadly, that theorem, I'm just writing it here, but in a graded version. So K0 graded of L of P, if this would be isomorphic to graded of L of F, and under this isomorphism, the positive cone goes to positive cone. And also this is specific graded module would be sent to this one. So, i.e. the claim this invariant is a complete invariant for Leavitt path algebras.
So are these Leavitt path algebras of finite graphs ultra-matricial?
No.
You're just making
No,
and
yeah.
we're talking
There are examples of graphs that the Leavitt path algebra becomes ultra-matricial.
Yeah.
but the more interesting ones are not, in fact.
Excuse me. So in this case, okay, so in the previous case of matricial algebras, the last part were the generators. So it was basically one going to certain one, right? Because when you go in K-theory to MNF, the one in MN0 keeps shifting its position. That's why they wanted to keep trace of one, I think. So here, what is the meaning of isomorphism of LE in those components existing also? So in this, what do you mean by this triple is isomorphic? So first two is that they are isomorphic as groups and semi-groups. And what is the
This
part?
one?
Yes.
Oh, okay. So that means you have a map. Okay, right. So you have a map. It's good you asked me because I forget to say one part of it. So you have a map, which under this map, this element will be sent to this. So you have a map, and this is one element of this group. This should be sent this way. But what I forgot to say is that as modules, because remember these are not only groups, these are modules. So I really want the shifting also be preserved. All that means is that if you have this goes to this, and if you shift this a bit, then this has to go to this. That's what it means being the shifting is preserved.
I see that looking at the grading of MNF you defined yesterday, it seems that even this last part is not even necessary. Or is there a counterexample? So I mean to say that just saying that the graded K groups are isomorphic should be enough, because the grading should take care of LE where it goes.
No. I mean, the exact same, I really need this bit also in that setting.
Okay.
Because look, you really need this because, first of all, look at this example I gave this today. Maybe something. You can prove that there is a graded Morita equivalent between this and K. So now I'm looking at the graded category. Then I'm going to do the same trick. Maybe I put F here so that it does not. So if you look at the graded modules over this, so the category of graded modules, I write GR of that. There is a Morita equivalent between this and then this one here. Therefore, the graded K0 is the same as the graded K0 here. So the same here. So i.e., first of all, it doesn't see this 5 again. That's why it takes into account this one. The second thing is that if I just use graded K0, it doesn't matter what is here, I end up always with F. So it doesn't, graded K0 in itself does not see the shift. That's why I need to put this. All right, so the rest, so I have a bit of time, so I'm going to show you really how this K0 graded is related to a lot of things in a different subject. It's pretty nice. So let me just use now the beamer, if I can.
Can I ask why do you give it for the conjecture? Why are you saying finite?
Oh, okay. So that's a good question.
Identity for one.
So the reason is, if E is finite, then the Leavitt path algebra has an identity. Right? And then it makes sense to talk about this. So if the Leavitt path algebra doesn't have an identity, then K0 is defined differently. Because then projecting modules, if your ring doesn't have an identity, then for projecting modules you have to work a bit harder. But then you have to replace this a little bit.
local units to do.
Yeah, so with local units, but again, you don't have this really. And then you, actually this has been worked out by Goodall in the standard case, and instead of this, he puts an interval. So he says there's an interval. If that interval goes to that interval, then you are good. And I would imagine the same version should go through. I'm just going to show you how this graded K0 would be connected to different things. And you might have heard this story before. Some of you might have heard this story before. But really, it's a very nice story. So let me just go ahead and tell you. So I'm going to, first of all, start with some relations, very simple relation among matrices. In fact, these are so simple you can describe it to high school students. But very quickly, you can ask questions that are open. Nobody knows. So, start with two matrices, and these are n by n matrices, so they are just sort of square matrices, and you fill it with non-negative integers. Okay, 0 could be in there, and non-negative integers. So you have 12. Then I'm going to define some sort of a relation between them. So I say A and B are shift equivalent. Oh, let's see. Oh, I should go back. Oh. All right, so I'm going to say that A and B are elementary equivalent if this happens. If you find two other matrices that R times S gives you A, if you flip this, you get B. Look, A and B are square matrices, but R and S could be rectangles also. Okay? So let me give you an example. Suppose A is a 1 by 1 matrix, 2, and B is a 2 by 2 matrix stack. And I'm claiming that A and B are elementary shift equivalent. I'm claiming that. That means you have to give me now R and S. So that's the R and the other is S. Okay? So I just proved that A and B are elementary shift equivalent. Great. So now, I'm going to also define strongly shift equivalent. Okay. So what does it mean being strongly shift equivalent? A and B are strongly shift equivalent if I can find a chain that the first starting from A, the next one is elementary to A, the next one is elementary to A1, the next one is elementary to A2, and then I can reach B. Okay? So i.e., this is your A, this is your B. I cannot go from A to B in one go. So there is no R and S, then RS gives me this, SR gives me this. So I have to go step by step. So if I want to put this in a more intelligent way, I would say that you have elementary shift equivalent, and I'm generating an equivalence relation, and that's it. So strong shift equivalent gives you an equivalence relation between matrices. Let me give you an example now. You have these two very, very sort of innocent-looking matrices here. A is this and B is that. And my question is, if A and B are strongly equivalent, so you have to give me this chain and R and S. All right, so let's start. This is the first R and S. Then I'm swapping this, and I get A1. Okay. So now A and A1 are elementary shift equivalent. So now I have A1. I have to find another R and S, and that gives me A2. Good, so I go one step further. Now I have A2, find other ones, that gives me A3. Now if you wonder where I bring these numbers, well, I wonder too. That's just in itself a paper. Somebody worked this out using a computer. Okay. So now I'm here. I'm in this step A3. This is A3. This is your R. This is your S. Just go flip them. You get another A4. A4, A5, A5, A6. Now, good. So I'm here now. So A6 is elementary to A5, A5 elementary to A4, here. So I'm here. I come up with two other matrices. You see they are getting smaller. And then I arrive to B. So I just proved that this one is strongly shift equivalent to this one. All right. So this, as I said, this computation was one paper, and it's not known if just to give you how complex it is, it's not known if I can reach from here to here in shorter steps, fewer steps. It's not known. In fact, what I just proved, I proved that if you plug 3 in here, then you get strongly equivalent matrices. And it's open if you just put 4. So as you see, 5 or 6. As you see, you can describe this to a high school student and just right away ask this question. So now, the first thing is that, can you come up with a complete invariant for this? So again, if I hand you 2 matrices A and B, would you be able to tell me very quickly if they are strong shift equivalent or not? Can you come up with some sort of noise invariant? Good. Now, so I define elementary shift equivalent. I define strongly shift equivalent. So let's define shift equivalent. So now, A and B are matrices. You fill it with non-negative integers. Now, what is the shift equivalent? Again, if you find R and S, could be rectangles, such that this time R times S, well, you don't recover the whole A, but you recover some power. And if you flip them, you recover the same power for B, and you have some sort of a commutativity here. So if it happens that R is invertible, which oftentimes is not, if it happens, that means A and B are conjugate. But some sort of a commutativity here. So this is the definition of A and B being shift equivalent. So these 3 conditions, what are the relations between them? So where do they come from? So there is this subject called symbolic dynamics, and I've started learning that. It's really a beautiful subject, and I just wanted to write a book that you can have a look. It's a fantastic book. By Lin and Marcus. It's called Introduction to Symbolic Dynamics. It's a great book, and if you know David Pask, in one of his talks, he said that this is such a nice book. I've lost 3 copies of it already. So he always carries the book with him.
One question. Maybe it looks like we should call strong as weak, no?
Yeah,
I mean,
that's right.
I mean, the thing is that the strongly shift equivalent implies weak. So that's what you get. Right. Right. Weak. Sorry. Yeah. Right. So weak gives you strong. Yeah. Why do they do it that way?
let the meek shall inherit the earth.
Right. So of course, sorry. Weak equivalence gives you strong shift equivalence. I never thought about this. Why in the next thing you see that somebody called Williams named all these.
While we're waiting, let me ask another question. Can you give us the reference? We can give it later of that paper which they calculated all these numbers between this equivalence of the shifts.
Here also it's in this book.
Well, they calculate.
He brings that paper in this book and then gives a reference. So you can explicitly see these calculations
they
that I
do
put
the
here from this
calculation.
book. Yeah.
And another thing, when they did this like elementary shift move, it looks like they are doing the outsplit. Is that correct?
It's the next slide.
Okay, outsplit.
Yes, exactly. So now,
Is there an algorithm or something?
the thing is that we don't have any algorithm, and we don't have any complete invariant for strong shift equivalent. Yeah. So that comes in the next.
Any invariant known?
No, but I mean, it comes. There are some invariants for some cases, and you'll see that. Okay, first of all, where do they come from? It comes from this paper of classification of shift of finite types. Of shift of finite type is the objects that you study in symbolic dynamics. Okay, so he's studying this, and he realized that instead of working with this stuff, that it takes a semester to introduce shift of finite type, you can actually look at matrices And if two shift of finite tops, whatever they are isomorphic in that category, it boils down to saying that the matrices are strongly shift equivalent. So that was his sort of, that's why it's a very important paper, that he basically reduced working on this stuff to working with matrices. Okay, so now, as you mentioned, if A and B are elementary, first of all, you can prove that it's strong, and you can also prove that they are shift equivalent. So let me just maybe put this together so that. So elementary shift means you have A gives you RS and B gives you SR. Just shift means you have again some R and S gives you some power of A, some power of B, and then you have to communicate. I want to get this right. AR is RB and so on. So in the paper, first of all, he proves that if you have elementary, you have this. Well, that should be clear. Let me see if I can do at least this bit. So if R and S gives you A and S and R gives you B, you pick R being 1, then I have to check this bit now. Okay, so A, let's see if I can get it. AR is the same as, instead of A, I put RS. So RSR. Now instead of RS, instead of SR, I put B, so I get R. So this is. So elementary gives you shift. Now, the next thing he proved in this paper is that strongly shift equivalent gives you shift equivalent, and shift equivalent gives you strong shift equivalent. So these two concepts are the same. Remember that strong is that you go from A to B via these elementary ones. And then the next year, he realized that he made a mistake. Yeah, and then he cannot prove that if it's shift equivalent, it is strongly shift equivalent. He could not prove that. And in the paper, not only he found the mistake, he could not fix it. So, and then it took 20 years for two mathematicians, Kim and Roche, to give a counterexample to this, that in fact, it is possible that A and B are shift equivalent, but they are not strongly shift equivalent. And I look at this paper, and it's not like they give you two matrices and say these are the matrices and they don't do that. They go through CW complexes, algebraic topology, so on and so forth, and say if that happens, one main theorem in algebraic topology fails. So it's not very easy. Okay. So now, here is where Muge mentioned. So there is a way to attach a graph to a matrix, and you know that, the adjacency matrix. And then instead of working with matrices, I'm going to work with graphs. And that's also in his paper. So I'm just skipping this. So now, this is adjacency matrix. This is a graph related to this matrix here. And in fact, if you think about this, if I give you a matrix which are all positive, you can always translate it into a graph. And if you have a graph, you can always translate it into a matrix. So these two really have the same information. The matrices with positive entry and the graph. So the same information. So if I give you this, do you know what sort of graph represents that? It's a cycle. Okay, so now, in the paper, Williams gives you two moves or two ways to change a graph. So you start with a graph. He called it outsplitting. You start with this graph. You follow some procedure. They are not very difficult. And you get a new graph. Two different ways. I'm not going to go through that, but I'll just show you some pictures. So if you look at this graph and you plot it into that outsplitting procedure, you get this. Of course, if your graph is more complicated, then what you end up with is also more complicated. All right. And here is the punchline of his paper. He says that A and B, these two matrices, remember, with all that computations, are strongly shift equivalent. Okay, here, strongly shift equivalent. You go from A to B. If and only if you look at this as a graph, right, I can translate this matrix as a graph. I look at this also as a graph, then you would be able to start with A, do this in splitting and out splitting, keep changing this graph, and reach to B. So instead of working with just all that numbers, I can work with pictures. And this is an if and only if. Great. So now, Suri asked me about invariance, of course, so let's see if I can come up with some invariance that quickly tell me if an A and B are shift or strongly shift equivalent. Alright, so let's start with an A. So this is, again, a matrix filled with non-negative integers. So now, look at this one here. A is an n by n matrix, so you can think of this as a homomorphism from Zn to Zn. It's a homomorphism, this is a abelian group, so now keep doing this. Again, another homomorphism, so you get a sequence here, so you are allowed to get the direct limit of this sequence. You get some group. Alright, now, just put the same sequence down here and fill this diagram with everywhere you go, you're just applying A. So a commutative diagram here, a commutative diagram here. So on the level of direct limit, it gives you a map. Okay. So far, starting with A, so I just started with one A. Now I have one group delta A, and I have this map. I need one more gadget. Now, if you start with all the positive numbers, so n to the power of n. Look, this is filled with positive numbers also. So when you multiply this with the positive, you go again to n to the power of n. Okay? So this sends n to the power of n to n to the power of n, and then get the direct limit. So now you're working with the monoid, but you have a direct limit there. So you end up with some monoid here that I call it the positive cone of delta A plus. And here is the punchline. That A and B are shift equivalent, here is the definition. If and only if you calculate this delta A, you would be able to produce an isomorphism from delta A to delta B, which sends the positive cone to positive cone and commutes with these maps. So if this happens, then A and B are shift equivalent. Now, mind you, there is a trap here. I know these are difficult stuff. Here it translates to delta A. It's not very easy if I hand you a matrix to give me this direct limit. And I haven't found any here. Even if I can give you a very simple matrix here, and you might struggle to give me this group. So the difficulty is passed to this one. Okay, let me summarize what we have done so far. So strongly shift equivalent here, the definition that I go from A to B via these elementary ones. I have a graph characterization for that out splitting, but no complete invariant known. And people are telling me it's quite an active subject. People are trying to find complete invariant for this. Then we have the concept of shift equivalent. No graph characterization known. Still not known. But you have a complete invariant. It's called the Krieger's diminishing group, that thing here. All right, so let me put this diagram here. These stuff here are these shift of finite types that I haven't defined. They appear in symbolic dynamics, but the genius of Williams was that you can translate into these matrices. I'm talking about strong shift equivalent. On the other hand, you have shift equivalent, and then Krieger gave this complete invariant. I know that from stronger shift equivalent, it implies shift equivalent. I know I can go this way. I know I cannot go the other way around. That was the Williams mistake. I cannot go the other way around. So now, can you put more stuff in here? Can you complete this a bit more, put more information in here? And this is where the Leavitt path algebras comes in. So I just show you the field diagram. First of all, I want to remind you of this conjecture here. Remember, we had a conjecture here, the conjecture that two Leavitt path algebras are graded isomorphic if these graded K theories are the same. In fact, you can prove this for a class of algebras, a class that you can call it multi-headed one. So you see, you have a graph that always ends up in some loops or cycles. if you have a formal definition, of course, for this graph. But if your graph looks like this, then in fact, K0 would classify. And there are partial results here that some weaker version is correct for finite graphs. So now, let's go here. So Williams said that if you have two shifts of finite types, they are strongly shift equivalent. Now, it turns out that, look, these are now matrices, right? This is a matrix assigned to this graph E, this is a matrix, and this is a matrix. And now, let me go backward. Let's try again. So you have shift of finite types, and Williams said that you can assign to this shift of finite type two matrices, right? And if they are conjugate in the category of shift of finite types, whatever they are, here you have a strongly shift equivalent between matrices. Now, look, this is a matrix. I can assign a graph to it. This is a matrix. I can assign a graph to it. So this is this bit. Now, this graph that I assigned to this has a Leavitt path algebra associated to that. This matrix has a Leavitt path algebra associated to that. If these are strongly shift equivalent, you can prove that these two Leavitt path algebras are graded Morita equivalent. So that is in the paper that you can prove. So let me just write it down here. So if A and B are strongly, A and B are strongly shift equivalent, so if you look at the Leavitt path algebra associated with the graph here, the category of all graded modules are equivalent. So these two categories are equivalent. Great. Now, if two categories of modules are equivalent, then all these invariants that you built out of linear algebras, including K groups, are the same. So the K groups are the same. Now, this is the punchline that R and Pardo, and in another paper, you can see that, in fact, this Krieger's dimension group happens to be exactly the graded K theory of the Leavitt path algebra. And not only that, the positive cone is the positive cone here. And that, you remember that you have a map which commutes here, remember that delta A, that happens to be matching with the action of X on this one. So you see, I actually built a bridge. I started from here, and I could say that if you have this, you can go all the way and get this one. But I know that from here you cannot get there, so somewhere has to, the backward might not, okay, I skip that. There's a conjecture that this goes also true, this bit also goes true, but apparently this part would break. So i.e., if these two Leavitt path algebras are graded Morita, you cannot then say that the matrices associated to them are strong shift equivalent. So I'll just leave you with these two conjectures. One is that graded K theory would classify Leavitt path algebras completely if you have all the gadgets. And if you just have this bit, then maybe they are not isomorphic, but they are graded Morita equivalent. Thank you.
Are there any questions, comments? I have a question. The splitting, they are not graded isomorphic, but can we still say that from the strong shift equivalent to matrices,
Right.
that they are isomorphic as Leavitt path algebra?
Yes, in fact, you can prove that if you go from E to F via outsplitting, on the level of the Leavitt path algebras, they are graded isomorphic. So, I mean, Gene Abrams and Pardo show that they are isomorphic. You can build on their proof and show that, in fact, they are graded isomorphic.
So only if you use outsplitting,
Yes.
the isomorphism, but if you do in-split,
Very good. So if you're doing splitting, in their paper, they show that they are Morita equivalent.
that's all.
Now, you can build on that and show that, in fact, it's more. It's graded Morita. So, by the way, graded Morita equivalent implies Morita equivalent. So, you can go through their proof and check that, in fact, there's more valid, namely, they are more graded Morita equivalent. That's why I can build this bridge with graded case here.
I have another question. What about the shift mode? Does that occur over here? I mean, you mentioned about in-splitting and out-splitting, but if we do a shift move, shift also preserves the isomorphism.
Oh, okay. No, some of the moves would not do the grade, would not give you the grading. Yeah. But yeah, that's a good question. Look, when you do this move, changes in the graph, some of the changes you do, for example, just very quick one. So you have this cycle, right? So you can collapse this cycle to this loop. And the Leavitt path algebra of this is Morita equivalent to the Leavitt path algebra of this. And in fact, if you think about this, if this is just M2 of f, and this is just, I don't know, M2 of f x minus 1, and this is mfx x minus 1. So they are Morita equivalent. So you can collapse this to this one, sort of shrink this, and they are Morita equivalent. But here, they are not graded Morita equivalent, and the indication is, look, this is a cycle of length 2, and I'm assigning a length 1 to it. So I'm changing, the grading changes, and it makes sense that this would not go through, and it's not going through. So some of the moves that you define would not preserve the grading, but some would, including out-splitting and in-splitting.
Any other questions?
My question actually is behind the screen. I can ask it to Roos just later. Well, it's kind of related to the question I asked, I think, yesterday. Namely, you see, you have your conjecture, and now you're using a specific grading. It's a grading that's, you call it, I guess, the canonical grading?
Right.
Okay, so the gradings you talked about yesterday come in families. You have a grading of a specific kind. So, if you have your canonical grading, and you have an isomorphism, does that imply if you take a grading of a different kind, then you also get an isomorphism?
Good question. Off the top of my head, I would say no, but
Okay, but
good. That's a good question. Yeah.
But if that question can't be answered positively, this conjecture is false.
Why?
Well, because of the following. Namely, if you grade both sides and they're of the same kind, okay? Then it seems to me, if you have an isomorphism here, then you should also get an isomorphism if you just change the kind.
Yeah, that's what you were asking me first. So imagine you have a canonical isomorphism, and it would give you for any other grading an isomorphism.
Yeah.
So suppose we have that, and then what happens?
I mean, if you don't have that, this conjecture is very likely to be false.
I see what you mean. So, okay. So imagine it's valid for canonical grading. Then I change the grading to say Z2. And imagine it's valid there also. Then that should imply that the Leavitt path algebras are graded isomorphic as a Z2 grading.
Yeah,
Also.
for example.
So that means the Leavitt path algebras are isomorphic over any grading. And that might imply that it's wrong.
Yeah, and that's not true.
Right.
So that might be even an easier conjecture to prove. Namely, if it's isomorphic over the canonical, then it's isomorphic over any other grading. That wouldn't prove that the Leavitt path algebras were isomorphic, but it would be evidence towards that. And if that were false, then your conjecture would be false.
Yeah, so maybe let me just write this down. Again, off the top of my head, I will say that you cannot do, but so what you are saying is, so fix gamma and then the Leavitt path algebras is gamma graded, then instead of this, I just put gamma. That means I'm working with in the setting of gamma graded. And you say that, would that imply that I get sort of some other things? Would that imply this?
Yeah,
And I would imagine the answer is no, but yeah.
well, but I was thinking a bit more specifically, namely, let's suppose your gamma is your canonical grading, and then your omega is some other grading.
Right, okay, so I put here just this. Right.
Do you get that?
My conjecture is perhaps not.
Right, I would imagine also, yeah. Yeah, but this is a good question, yeah, I never thought about that, yeah.
And this suggests maybe that the K theory is superfluous. Namely, what one could simply try to do is to prove that if the Leavitt path algebras are isomorphic under all families of gradings, okay, then they are, let's see, no, okay, I take that back.
Right.
Any other questions? So let's thank Professor Roozbeh again. We'll have tea break now and we'll resume at noon, unless you want to
Hello, on behalf of the organizing committee, we have Professor Roozbeh Hazrat, not only for his excellent lectures, tutorials, and today he has a tutorial. Yeah. So, but apart from that, he has many other contributions for this workshop, and I would like to share something with you people because some participants are here and maybe they will follow this path in future. So in 2015, I just applied for SIMPA Research School here in Turkey as a participant. And I was not expecting some of the I could attend that, and got the SIMPA support from there. And there, Professor Mercedes, who will speak in the next week, suddenly she told that, okay, so you can also introduce this subject in India. I said that, but I don't know the subject. So she said, but both the things you can do together. So I said, okay, I was feeling very shy and not confident. And then I said, Roozbeh, that she is telling like this. I said, do it, I'll be there. And then actually he was there throughout me, and he suggested me regarding many who will be the speakers and etc. and tried to gather them, and for many other suggestions. So I thank him for everything, and hope you have enjoyed, and please catch him.